Welcome to this lesson on polygons and their internal angles. A polygon is a figure with straight sides that intersect only at their endpoints. Some shapes that you may already be familiar with are the triangle, a quadrilateral, and a pentagon. What these shapes have in common is that all their sides are straight and they intersect only at their endpoints. If I have a shape such as a semicircle or a half moon, which contains one side that's straight and a curve, that is not a polygon. I could also have a shape that looks somewhat like an hourglass. Even though this shape has all straight sides, they intersect at this point in the center. So that is also an example that is not a polygon. Convex polygons have no sides that contain a point on the inside of the polygon. Students often think of this as they do not cave in on themselves. So these three examples here would all be examples of convex polygons. Some other shapes I could have are concave. These contain sides that may have points on the inside of the polygon, and yet they still count as a polygon. So for example, I have the star shape, in which I have all straight sides. They all intersect at a endpoint. However, if I were to connect the outermost points of this shape, I would find that I have points inside. So in other words, if I were to connect these, I would find that I have sides inside the polygon. That is a concave polygon. A very special type of polygon, which we will work with extensively, are regular polygons. What's special about a regular polygon is that all the sides are congruent and all the angles are congruent. So all same sides are the same and all the angles are the same. In classifying polygons, we do have special names for a few of them. I'm sure that you're already familiar with the triangle, which has 3 sides, a quadrilateral, which has 4 sides, 5 sides is a pentagon, 6 is the hexagon, 7 is the heptagon. We also have names for the octagon, which is 8 sides, 9 sides is the nonagon, not the ninagon, that's an N-O, nonagon, 10 is a decagon, 12 is a dodecagon, and after 12, we tend to just use the term n-gon, in which n is the number of sides. So generically, we could say a figure is an n-gon if we didn't know how many sides. If I knew that a figure had 15 sides, I would call it a 15-gon. If a figure had 100 sides, I would call it a 100-gon. There are additional special names, such as a figure with 11 sides is sometimes called a hendecagon and sometimes called an undecagon, but generally the ones in this table are those that are most common. When working with polygons, it's important to keep in mind whether the angles that you are interested in are internal angles or external angles. An internal angle are the angles that are on the inside of a polygon. The exterior angle is formed when we extend the side of the polygon and we measure the angle that is created on the outside. We're going to take a look at some of the special properties of polygons regarding their angle measures. Today we're going to look at the interior angles of a polygon. All the figures drawn across the top here in black are polygons. And I'm sure that you're familiar, with most of these. So the general black lines here are the actual polygon. And inside, I have drawn diagonals across the polygons joining endpoints. In this first shape, I have a quadrilateral that has 4 sides. When I connect all the vertices, starting from 1 and going in order around the shape, I create 2 triangles. In this pentagon, if I start with this point and I connect one at a time to each of the other 4 vertices, I find that I have 5 sides and I can create 3 triangles. In this heptagon, I have 7 sides, and when I draw my connecting lines, I create 5 triangles. In this last example, I have an octagon. It's not a regular octagon, but it does have 8 sides, so that makes it an octagon. And by starting with one vertice and connecting to all the others, I create 6 triangles. So, in looking at this information, I can know how many sides does a shape have in general. If I had an n-gon and I don't know specifically how many shapes, I would say that it had n sides. How many triangles can I draw starting at one vertex in each shape? That's what I've done up here. The question is, how many triangles can I form? Did you see a pattern? 4 sides gives me 2 triangles, 5 sides gives me 3, 7 gives me 5, etc. So the number of triangles that I can draw would be n for the number of sides minus 2. If I consider the sum of all of these angles for each of these shapes, a quadrilateral has a sum of 360 degrees. A pentagon has a sum of 540 degrees. A heptagon has an internal sum of 900, and an octagon has a sum of the interior angles of 1080 degrees. The sum of the angles of a triangle each has 180 degrees. Therefore, it's not a coincidence that my sum of the interior angles is the number of triangles times 180. So 2 triangles times 180 is 360 degrees. 3 triangles, 1, 2, 3, times 180 is 540. 5 triangles times 180 is 900, and so forth. So how many degrees does each of these shapes have? I simply take the number of sides, I subtract 2, and I multiply by 180. This is the sum of the measures of the internal angles. As long as a polygon is convex, the sum of these angles will always be S for sum equals n minus 2 times 180. This will work for any size polygon. In theory, you could have a polygon with 999 sides, and you could figure out the sum of the internal angles.
Oops!